Yesterday we ended off and we had talked about closed air columns. Okay, and I'd shown you how that worked. Okay, with the tube and the tuning fork. And the big thing about closed air columns was that when they are resonating at their fundamental frequency, this is the waveform that we get forming in the tube. Okay, that represents 1/4 of a wavelength. So if I take the length of the tube and multiply it by 4, that will give me the wavelength. So this is the formula for closed air columns resonating at their fundamental frequency. All right, so if we run into any problem solving to do with that, that's the formula that we would use. The other thing we need to remember about closed air columns is that they only resonate at which frequencies? Okay, this is F1. Okay, F2 has a waveform that looks like this. If you recall, when I was lifting the tube out of the water, it got loud and then it got quiet. Okay, so this is F2. This is F3. F4 looks like this. So closed air columns only resonate at odd numbered frequencies. They only resonate at F1, F3, F5, F7, and so on, okay? Because even though there's a waveform in the tube at F2 and F4 and F6, it doesn't make any noise because there's what at the top? A node, right? Okay, so even though there's a standing wave pattern, it doesn't resonate there. Okay, so it won't make any sound. That might be important in case you get an exam question or something like that that says, you know, here, calculate all this stuff for a closed air column at its fundamental frequency, and then it asks you, what's the next frequency you would hear? Instinctively, we would say F2, except that, did we hear anything at F2? No, the next frequency we would hear would actually be F3, okay? And so we need to make sure that we could calculate F3, okay? Everybody all right with that? Okay. Now, open air columns work similarly, but they do have some important differences. Okay, so an open air column is open at both ends. The reflection of the waves actually is off the interior of the tube, not off the end. Okay, so we get a very different type of wave pattern forming. Well, not very different, but we get a wider range of wave patterns forming. Okay, and that is why for an open air column, we get resonance at all frequencies. F1, F2, F3, F4, all of them resonate because there's never a time where there's an antinode at the end. Sorry, I was waiting. I thought you had one more. Bless you. Okay. Everybody kind of follow me on that? Okay, so open air columns have a much wider range of sounds that they can produce, which is why we use them more often for musical instruments. Okay, basically all of your wind instruments, okay, that you would see, like a saxophone or a flute or a tuba, okay, any of those kind of things, they are open air columns. They're open at both ends. Okay? In order to make different notes, all we do is change where the air escapes. Okay, that is, we change the length of the air column that's going to resonate, and that produces a different wavelength and thus different frequency of sound. And you do that by pressing the different keys, okay, or covering up different holes with your fingers if it's a flute. Okay, that changes the length of the air column that resonates. Everybody follow there? Okay. So, big thing with open air columns is that both ends of the tube are open. Okay, so they resonate at all harmonic frequencies because there's never a node. Okay. So for the fundamental frequency of an open air column, we get this waveform. Okay, this is F1. How many waves are in there? Half. There's half a wavelength in the tube. Remember, an entire wavelength looks like this. Okay, that's an entire wavelength. That's a quarter, that's a quarter. The distance between them is a half, and that's exactly what we see inside of there. All right, everybody okay with that? All right, so at the fundamental frequency, there's half a wavelength in the tube, which is why the formula for open air columns, which you will need to add to your formula sheet if you still have your original one, okay, is lambda equals 2L, because there's half a wavelength in there instead of a quarter like there was for the closed air column. Okay, and then you can see, okay, in the next one here, we have a full wavelength in the tube, okay, because here's a quarter, there's a half, there's another quarter, that's a full wavelength. Okay, in this one here, there's a wavelength and a half. Okay, and in here there's 2 full wavelengths. All right, so unlike the other one that went up by a quarter of a wavelength each time. Okay, so here was 1/4, here was 1/2, here was 3/4. Okay, we're getting every half a wavelength here. Now, in actual fact, on this one, we only hear sounds every half a wavelength, okay, because that's how far apart the antinodes are. Okay, if you're adding another antinode, then you have to add another half a wavelength in the tube, regardless of which type of tube you have, right? Okay, is that making sense for everybody? Okay, so we're going to kind of look a little bit at problem solving here. How do like air column kind of problems work? Okay, so that we can have some understanding of that. All right, so let's have you copy this one down. I'll give you a minute here to get a copy down, and then we'll work through it. All right, so just so you're aware, I wouldn't ask one like this because I don't like the vagueness of this question. Okay, but it's still worth looking at as kind of an example of an air column question. So what we have here is we know that the tuning fork has a frequency of 384 hertz. Okay, and they're telling us that the speed of sound is known to be around 300 meters per second. That's what I don't like about this. I don't like when questions say around something. That I don't like that. Okay. But that's what we're going to go with. They're saying the length of the air column that's resonating is 0.675 meters. They want to know what's the possible wavelength for that data. Okay, what are some possible wavelengths? In other words, they're asking which situation is going on here. Okay, is it like F1, where we have 1/4 of a wavelength in the tube, or is it F3? Where we have 3/4 of a wavelength in the tube. Whoa, I got kind of wonky. Okay, or is it even F5? Okay, where there's 5/4 of a wavelength. I didn't do that right. I should have started at the bottom. Start over again. That's better. Still wonky, but you get the idea. Okay, so it could be any one of those three is likely. Okay, so what I want to do is figure out what's the wavelength of this sound. Would it come out to a speed of around 300 meters per second? What's the wavelength for this situation? Would it come out to a speed of around 300 meters per second? That's all I have to do is I just have to do some process of elimination kind of stuff. All right, so if this is the situation, then my actual wavelength is going to be how many times this number? 4 times this number. Okay, so we'll take 0.675 and multiply it by 4. So that's the wavelength, 2.7. All right, I'm thinking that's probably not it. Why am I thinking it's probably not the right wavelength? Because if I manipulate, if I'm doing this, V equals F times lambda, and I already know F is 384, if I multiply that by 2.7, I am not going to get 300 meters per second. Right? I'm going to get like 900. Right? So it's probably not that one. Agreed? Okay, so we've eliminated that one. If it's this one, then 0.675 meters equals 3/4 of a wavelength. Okay, so I'm going to take this number and I'm going to divide by 3/4. Okay, I like that one. I think that might work out. Okay, it's saying that the wavelength for this situation would be 0.9 meters. All right, so if I do that and I multiply that by 0.9, that's going to be a lot closer to 300. Agreed? Yeah, 345. I'd say that's pretty reasonable for a speed of sound in air. If I do this one, it's going to be too small. Okay, you guys follow what we did there? Okay, so all we did was take the length of the air column and use it to figure out what the speed of sound would be. So why did you divide it by 3? I didn't divide it by 3, I divided by 3/4. right? Basically I said 0.675 meters equals 3/4 times lambda, because it's 3/4 of a wavelength. Then I divided both sides by 3/4. It said the speed of sound was slightly greater than 300 meters per second. So all we had to do was come up with one of these wavelengths that was going to give us a speed of sound that was reasonable for air on Earth. Yeah. Okay. All right. Everybody okay with that one? Again, that was a bit of a convoluted question. Okay. Let's try number. No, I don't like either of those. They're like this one. Okay, try 3 and 4 here. These are standing waves on a spring questions as opposed to air column questions, right? So remember how that works. Okay, you may have to draw the standing wave pattern so you can figure these ones out. Okay, give you a little bit of time on that. We'll make it a little bigger so you can see it. Okay, answers are down below here. Okay, so for number 6, we have a standing wave generated in a spring that is 6 meters long. All right, so we know the length of the spring is 6.0 meters. Okay, the standing wave pattern consists of 3 antinodes. Okay, so there's going to be one end, there's going to be the other end, and I'm going to have 3 antinodes. All right, how many wavelengths is that? 1.5. Okay, it's 1.5 wavelengths. So if 6 meters equals 1.5 wavelengths, then I take 1.5 over to this side and I'll have my wavelength. Agreed? So my wavelength is 4 meters. All right, that's what I have to do with that initial piece of information. I have to use it to get my wavelength. All right, now that I know that, I look at this and it says the frequency of the wave is 2.5 hertz. Okay, what's the speed of the wave in the spring? V equals F times lambda. 4 times 2.5 should give me 10, right? Meters per second. Oh, actually 10.0 because everything had 3 significant figures. But okay, everybody all right with that? How many people have done number 4? Okay, do we just need more time on 4 or do we need to go over 4? More time? Okay, more time. I see a few people nodding. So. All right, so when a spring is stretched to a length of 8 meters, the speed of the waves in the spring is 5 meters per second. Okay, the simplest standing wave pattern for this spring is that of a single antinode between 2 nodes at the opposite end. So basically it's F1, which means there's how many wavelengths on the spring? 1/2 of a wavelength. So if the spring's 8 meters long, the wavelength is 16 meters, right? That's what we have to get kind of out of that context. Okay, so what's the frequency that produces this standing wave? So we're looking for F, so V equals F times lambda. F will equal V over lambda, so that'll be 5 divided by 16, okay, which should give us our 0.313 hertz for our frequency for that one, okay? And what's the next highest frequency for which a wave exists? All right, that's F1. The next one is? This is a standing wave on a spring. Okay, it's going to make standing waves at F1, F2, F3. Remember that whole thing about only at odd frequencies is only for closed air columns. So the next frequency, like right now, they're saying this is the wave pattern that exists on the spring. What's the next frequency that would produce a standing wave pattern? It's this one. That's F2. Okay, F3 would have 3 antinodes in it. Okay, because this is waves on a spring, not a closed air column. All right, so we don't want to get our springs, closed, and open air columns confused because they're all different. Okay. All right, everybody okay with that? Which is why the answer is 2 times the first one. Okay, because F2 is 2 times, F3 is 3 times, and so on and so on. Okay, questions on how those two worked? Okay. All right, let's do this one together because this is an air column question, okay, a closed air column question, and see how we do with that. So we got a closed air column, resonates with a fundamental frequency of 256 hertz. All right, so I've got F1 is 256 hertz. Okay, I know it's a closed air column, so since it's at F1, that's the waveform I'm dealing with. my closed air column formula is that lambda equals 4 times the length of the tube. Okay, I'm looking for the length of the air column. And I'm told the speed of sound in that place is 343 meters per second. So, because it's at its fundamental frequency, right? All right, so if I'm going to calculate the length, I need lambda, okay? Because the only formula I have that has length in it is lambda equals 4 times L, and I don't have lambda yet. How can I get it? What can I do with these two numbers here? Right, I can put them in the universal wave equation, right? V equals F times lambda, so I'm going to have V over F to give me lambda. Those are the two numbers that I have. Okay, so we'll have 343 divided by 256. All right, so my wavelength's 1.3398 meters. Okay, now that I have that, okay, I'm going to find the length. So what do I have to do with this number? Divide it by 4, right? All right, so the wavelength for this one is 0.33 meters, or 3.35 times 10 to the minus 1, if we do that to 3 significant figures, which we should. Okay. Everybody all right with that one? Okay. Now, I'm going to do an open air column question as well, just so you've seen one of those. All right. So for this one, we have an open air column. It's resonating with a fundamental frequency of 256 hertz. So same as the last one, except this time it's open. Okay, we're looking for the length of the air column, again, if the speed of sound is 341 meters per second. All right, so this is an open air column at its fundamental frequency. That's what it looks like, because according to our thing here, okay, lambda equals 2L for open air columns at their fundamental frequency. All right, so can I do basically the same thing I did the last time? Yeah, all right. First thing I want to do is find lambda. Okay, lambda will equal V over F, so 341 divided by 256. Right, so it's again 1.33. Okay, and now I'm going to find the length. Okay, so length means I'm going to divide the wavelength by 2 instead of 4. I get that's bad luck, 0.666 meters for the length of the tube. Okay, on that question. All right, so they all work fairly similar. You just have to remember that for a closed air column, you're dealing with lambda equals 4L, and for an open air column, you're dealing with lambda equals 2L, and you're going to be doing some stuff with universal wave equation, and likely, once in a while, they might also give you the opportunity to use this formula. Right, they might give you the air temperature just to throw that in there as well. Okay. All right, going to have you work on a few of those. Okay, from the workbook here, just to make sure we get them. So in the workbook, it's all closed up to number 7, and then 8 and on is all open. So you might want to alternate. We did 1 and 8, maybe do like 2 and 9, 3 and 10, so on.